Right, everybody. Thanks for stepping in. My name's Bastian, and I'm going to talk to you about topology-based graph representation learning as part of the Oxford ML Summer School Unconference track. So this is a very loose and informal presentation format, and please feel free to interrupt me at any point if you have any questions or if you have any additional specifications. The only thing I would ask you is to mute yourself while I'm talking, and only unmute yourself if you have a question, because that reduces a little bit the background noise that I hear. All right, thanks a lot. And now let's get started. So you probably all know what graph classification is, but let me give you a brief example of that. So on the left-hand side, you see one graph. It has nodes and edges. And on the right-hand side, we see our target, which is, we have a set of potential labels, and we want to assign one of those labels to the graph. So that is the graph classification task, which exists in contrast to the node classification task, where we would be asking about, let's say, for instance, the label of this specific node. If we have a network that contains information about a business, for instance, we might be asking who's the manager here or stuff like that. But in this talk, unless mentioned otherwise, we will only be dealing with graph classification. So we're dealing with the broad picture and not the small picture. Now, to represent graphs, there are a few options, but already at the very beginning, we are kind of plagued by some issues with graphs in general. Namely, if we take two graphs G and G prime, they can have a different number of vertices. So in contrast to many other areas of machine learning, we can't just represent them with a fixed feature vector, but we have to come up with something better, or rather we have to learn some kind of vectorized representation, F, that takes a graph G from the space of all graphs and outputs a vector in some high dimensional space. Because otherwise we're not able to address the learning task. Of course, we could be using something like set functions, but in general, we need some kind of vectorized representation. We need to be able to handle the differences in cardinality of graphs. Now, the important thing about such a representation is that it needs to be a permutation invariant. Because there's no inherent ordering of graph nodes, it doesn't really matter in which order I specify them. So, of course, they have an inherent ordering if you specify them in a file and you read them out, but you could equally well just swap their ordering and it would still be the same graph. So this is really an important point to make. These representations need to be permutation invariant, and they need to be able to capture the full graph and not be contingent on any one specific labeling or any one specific ordering of graph nodes. Now, to give you a brief overview of graph neural networks in a very, very small nutshell. It's not a big nut that I'm talking about. Here's just a very, very tiny nut. The main idea of graph neural networks is that you want to learn an aggregation scheme over the neighborhoods. So you want to learn some kind of hidden node representation, HV, based on aggregated attributes of the neighborhood AV. Those are, as I said, aggregated over the node neighborhood. So you go to a node and you take its next neighbors that are connected to it, and then you iterate this process. So we'll be talking about more details in a second, but the main idea is you take all the neighborhood attributes, you iterate this multiple times, and then in the end you have a hidden representation that can be extremely high dimensional for every one of your nodes. And you can use this representation, you can collapse this representation in order to obtain a graph level representation. So this is similar, or this terminology is similar to the paper by Xu et al. Of iClear 2019, which is a great read, by the way. So it has my full endorsement on this channel or on this video. It's called How Powerful Are Graph Neural Networks? And it discusses the overall expressivity of a graph neural network. So the question of what can we actually capture with the graph neural network? We'll be returning to this later on. Now here, just three formulas that illustrate this concept a little bit in a pseudocode fashion. So to get these aggregated attributes AV in step K, we call an aggregation function, which is typically just a collection function and results in a multiset. And we use the hidden representations of the neighbors that we already had in the previous step. Then we combine them to obtain a new hidden representation, HV. And this combination is typically just an addition or an extension of the vector. And in the end, once we have all these hidden representations, we use a so-called readout function. It's called a readout function because it reads out the full graph representation at the end of this process. And this just takes all the hidden representations at the last step, big K of our process, and gives us back one vectorial representation with which we can do predictions. The classical readout function, for instance, could be a maximum function or a sum function, something like that. It's similar to a pooling function in case you're familiar with these sort of terminologies. Now, the overall or underlying scheme of all graph neural networks, or I should say most graph neural networks, is the message passing itself. So all this aggregation just works in the sense of passing messages between the individual nodes. So here, for instance, we have a very simple graph, and we assume that for every one of the nodes here, we have a d-dimensional attribute vector. So for instance, if we have just labels at those nodes, we could use a one-hot encoding, but in general, we can just assume that we have some high-dimensional attributes here. And now, if we want to do some message passing with v4 at our center node, we just take a look at all the neighbors of v4 in some random ordering, so v2, v3, and v5. We take their respective feature vector representations and aggregate them later on. Now, the nice thing is this aggregation can be, for instance, a sum function or a constrained sum function, something like that. We can repeat this process, of course, because once we have an aggregated representation of v4, nothing stops us to repeat this procedure multiple times. And this is exactly what we've been discussing on the previous slide. We repeat this process multiple times and always update our vertex representations accordingly until we obtain a readout function to obtain a graph level representation. That's kind of this thing in a visual nutshell. Now, let's finally come towards the second point of this talk, and actually I would say the main point of this talk, and this is how does topology come into play here? So some of you might already be familiar with some topological concepts, and they might be thinking about communities or modularity and these sort of structures. But here we're actually going one level down. We're not going one level up, I'm afraid, but we're going down to the very fundamentals. So taking this nice graph here, which is, by the way, a molecule from some data set that I forgot about, of course, we can calculate its so-called connected components. So that is, we can partition the graph into node sets such that all the nodes within one set are reachable by some path. Now, in this case, we just have a single connected component because every node is reachable by some path, and all pairs of nodes are thus in the same connected component. But if we would cut away, for instance, this edge here, the graph would be partitioned into two connected components. The number of connected components is also known as the 0th Betti number, and we denote this by beta 0. Now we can also go one step higher, and we can calculate some cycles. So cycles are what you would expect them to be. We just take a look at some structures that we can walk around and reach the start of our path again. Now here you can see that we have two different independent cycles. I should stress, in case you're already familiar a little bit with topology, these cycles are not unique. So the count, the number of cycles is unique, but not the way they look. So we could equally well have a cycle that goes around this graph here, these nodes here, and ends up here. But this, in some sense, are the most concise cycles that we can get. And the number of cycles is also known as the first Betti number, Betti 1 or beta 1 in this case. Now, let's step it up a notch. These counts are well and good, but they are not really that useful in practice, because it turns out that you can easily change them. If you add an edge or if you remove an edge, they always change. So the Betti numbers by themselves are not sufficient to do serious graph classification. But we can easily get to some better classification results if we suppose the following. Namely, we assume that we have some weights on the edges. So weights on edges give us a way to order the edges in some form. And now if we add all the edges in ascending order of their weight, we can watch as the topological features of the graph change. So we start with a graph that has no edges at all, and we start adding edges one by one, and we always check to what extent the topological features of the graph change. Now this is a lot to stomach, and I can't go into the details here because of the brevity of this talk, but there is a rich underlying theory here, and this is referred to as persistent homology. Homology referring to a topological framework that tries to assess manifolds or other structures by means of their connectivity. Now, the important thing for you to remember is that we need these weights, we need an ordering, and we can summarize the changes of topological features in a so-called persistence diagram. And we just illustrate this very briefly. The persistence diagram will contain a point at some position x, y, if a topological feature is created at a time step x of the graph creation process and destroyed at a time step y of the graph creation process. Let's walk through this and see what this means, and then we'll see that it's actually quite an intuitive notion of what to do with graphs. So we start with this graph and add a single edge. The single edge already destroys one connected component because previously there were two connected components here, but now there's only one, right? Because those 2 points are now in the same connected component. So we already have our first topological feature here. Now this process continues a little bit, and every edge that we add essentially destroys an additional connected component, except for this last edge here. So this last edge, something new happens here. This edge doesn't destroy a connected component because it already connects points that are within the same connected component. What happens here is now that this edge creates a cycle. We don't have a way to formalize the destruction or the creation of a cycle yet, but this is why I added a vertical line here, which is supposed to indicate that something new is happening and that we now have a cycle to keep track of. Now, as we continue this process, we see that we can get some more topological features, some more connected components are destroyed. And for the last edge, you can guess what happens now. For the last edge, again, we will get a cycle. And now the whole process is finished, right? So now the full graph has been created, and we have this persistence diagram on the right-hand side to account for topological features. But we forgot to account for a few of them, actually. And this is to do some bookkeeping. There are good mathematical reasons for this, which I can't go into the details here again. But to do some additional bookkeeping, we now add the initial connected component with which we started, because if you count the number of red dots here, you will find that one has been missing. So there's one less connected component than we initially thought. And we also add the cycles. So now everything has been accounted for, and we have this nice feature descriptor on the right-hand side, which summarizes this whole process. Now, to make this more formal, but I think this is the most formal we'll get, and then we'll just see some diagrams and discuss a few things. To make this more formal, persistent homology is a method or a framework that uses a graph G and some function on the graph's vertices, and it uses this to assign the graph a set of diagrams which describe the topological features of this graph as measured using this function f. So what does that mean? That means that we can use the function f as a kind of lens through which we view the graph and its creation process. And by not watching the graph at its last stage, so the full graph, but by watching the graph unfold or being kind of created through this lens, we're able to get a much more nuanced and much more detailed picture about topological features in the graph, which will serve us well for classification purposes. Now, in this diagram here, so just so you're familiar with the terminology a little bit, in this diagram here, the distance of every one point to the diagonal of this diagram is referred to as the eponymous persistence of a feature. This is where the method gets its name. The idea is that if you have a feature that is far away from the diagonal, it's probably super important for the graph, and so it's very persistent or very prominent if you want. Whereas if you have a feature that is very close to the diagonal, it's probably not that important to speak of. And this fact will become very relevant for us later on. Now, let me briefly summarize the status quo. And that is, graphs are, to my understanding and in my opinion, fundamentally topological objects. They have some connectivity, they create some connectivity, they even create some neighborhoods. But yet, current graph neural networks are incapable of recognizing certain topological structures. So for instance, there is a problem with graph neural networks in counting the number of cycles in a network. Their capability of doing so depends on their layer structure and on the number of layers and on the number of parameters. So there are some fundamental restrictions to what they can do and what they can see in a graph. So another question is, and this is, I would say, one of the core questions in my research agenda, what can we gain when imbuing neural networks or graph neural networks, to be more precise, with knowledge about the topology? Now we'll be delving into the first publication or the first preprint that I want to discuss. It's called Topological Graph Neural Networks, and it discusses essentially how to create topological layers for graph classification. And I should also stress for node classification, but then the title of the slide would be a little bit too long. So this is a preprint that we recently submitted to arXiv. It's work co-authored with Max, Edward, Michael, Eve, and Karsten, and I'm really excited to see this paper gain some attention and to be able to talk about this tonight with you. All right, to give you a brief overview of what we're about to do, and then I promise we'll be talking about the experimental details and what that all helps in practice. We'll have a general pipeline where we throw in a graph on one end and where we get an output on the other end. But the cool thing about this is that the representations that we get in between are compatible with downstream layers. So in essence, we can take a layer, such as a graph convolutional neural network layer, and we can replace it by our topology-based layer. And still the whole thing works. And the graph neural network is still capable to function and to perform its classifications, but suddenly it has access to all this topological information. So that's kind of the gist that I want to impart on you here. And to do so, we essentially follow a very, well, simplistic, I don't want to be too I don't want to be too strong here, but maybe I could say it's a very simple or elegant pipeline. We start with the node attributes of the graph on the left-hand side. Then we apply what we call a node map phi, which maps those node attributes to some k-dimensional space. And we treat this k-dimensional space as constituting k different views or k different filtrations of a graph. So if you think back of the function that I showed to you earlier on, this function f, that is supposed to characterize a graph, we now have this function, but k times. So we can learn k different representations of the graph. Each of these representations now gives rise to a certain set of these persistence diagrams, so these dotted diagrams that you saw before. And we use a so-called coordinatization function psi to create compatible representations of the node attributes. So the job of psi is to take one of those diagrams and map it back to a high dimensional space that we can combine by, for instance, summing or by concatenating and so on and so forth, that we can combine with the existing node attributes here to obtain a new node attribute x tilde of this vertex. And this, as you will see, is compatible with the original node attribute. So it has the same dimensionality, making it possible to, well, as I said, swap out layers for this layer here, and the graph neural network will be none the wiser. Why am I so much jumping around on this point? Well, the point I want to make here is that normally topological features also suffer a little bit from this curse of having different cardinalities. But in our case, we're capable of jumping around this problem and giving you back a node representation that is compatible with the original graph node attributes. I'm sorry, I think I saw a question there. Or did I misread that?
Yes. I was wondering how do you homogenize the different features in your diagrams to combine them in the aggregation step?
This is a good question. So we treat every diagram as an independent entity, and we learn a different coordinatization function psi to map that diagram into a high dimensional vector, or rather, I should say that we map all the diagrams at the same time to a high dimensional vector. And then we can just do this aggregation by summing the two vectors, essentially, or by having by applying an additional operation.
Yes, but I was wondering if, for example, if you having different numbers of connected components in the diagrams, do you take the maximum number of connected components and then fill with zeros or something like that?
Ah, okay. Oh yeah, I should stress that's an excellent question. That's an excellent remark. This coordinatization function psi is something that always results in a vectorized representation. We experimented with different functions there, but in the end, the function that we found to work best is a kind of deep sets function. So it treats this diagram as a kind of set, which in some sense it also is fundamentally, right? Because you can have different numbers of points. But being a set function, we can enforce an over representation because there's some aggregation step going on again. So we don't have to fill anything with zeros by ourselves, but we can train this full representation to learn a representation that is that works well. Does that answer your question?
Thanks. Yes.
Yeah, great. Happy to help. You're welcome. Right. So moving on, I want to briefly talk about the expressivity of a GNN. Again, not so many details here because of the brevity, but the interesting thing that Xu et al. Discovered in this iClear paper that I also mentioned on this slide again is that typical GNN architectures are actually no more expressive than the so-called Weisfeller-Lehmann test for graph isomorphism, commonly abbreviated as WL1. So this WL1 test is something that goes back quite some time. It has been originally described in the late 60s or late 70s even. And in the beginning in the beginning of the 21st century, some very promising and very relevant NURBS papers discuss the use of this WL procedure for graph classification. And in some sense, the WL test can be seen as the precursor to modern graph neural networks, because the WL test also has an inherent node aggregation and neighborhood aggregation scheme. The difference is that modern graph neural networks are capable of learning such representations or learning weights for the individual neighborhoods, whereas the WL test just treats all the neighbors as equal. But nevertheless, and this is a very important and crucial point that I want to make here, nevertheless, this test is still the upper bound for expressivity. So this means that if the WL test tells you that two graphs are not isomorphic, so they cannot be transformed into one another, then the best graph neural network can also not beat that test. So essentially, this is an upper bound for what the graph neural networks can detect. At least what some current graph neural networks can detect. It is possible to improve the expressivity in order to capture higher dimensional features or higher dimensional graph structures. But as I said, the typical GNN, so even something like a GIN or the classical GCN by Kipf et al., this will not be more expressive than the WL test. So why am I mentioning this? I'm mentioning this because in this preprint, we are showing that persistent homology and also our layer is at least as expressive as WL1. So essentially, we're showing that it's not worse than a GNN, which is kind of a nice thing to have. But we also show one thing more. We show that, in fact, there are non-isomorphic graphs, so two graphs that cannot be turned into one another. And WL1 cannot distinguish those graphs. So WL1, and thus also many current graph neural networks, would tell you that those graphs are the same. This is an example of those two pairs of graphs. So one has two connected components and the other one has a single connected component. Some or many graph neural networks are incapable of telling you whether you have two graphs here or not. The cool thing is, though, that persistent homology, so the method underlying our topology-based graph layer, is capable of assessing these two graphs. So it can distinguish between them. And this means that in total, we have obtained a layer that increases the expressivity of a graph neural network. Because recall that we showed before that it's at least as expressive as a GNN. And now we're showing that there are actually cases that a GNN can't handle, but that we can handle. So this means that we fundamentally increase the expressivity quite substantially. And here, this is a very simple example, of course, but it's also a very constructive one, I think. Here, these two graphs can be distinguished already by calculating very low dimensional Betti numbers. So on the left-hand side, for instance, we have two connected components, as I already said, but we thus also have two cycles, namely this cycle here and this cycle here. Whereas on the right-hand side, we have only a single connected component and thus also only one cycle. So this is a great outcome for us. So now, having established that theoretical, well, dare I say it, superiority of our method, let's also take a look at some experiments. And I want to stress that this is that we try to have a very stringent experimental setup here in order to make the most out of our comparisons. So we take a GCN architecture with 4 convolutional layers, mostly because this architecture turned out to be extremely useful and extremely successful in a recent graph neural network benchmark. Then we replaced the second layer by our topological graph layer, so-called toggle. And we also, but that's not super important here, and we also use a static variant of our layer that fakes topological calculations as a kind of ablation study. But I want to stress that the advantages of this network, so of replacing one layer and plugging in another layer, is that all the architectures that we are comparing, so at least the one that pertain to the GCN and the toggle, have approximately the same number of parameters. So essentially, we are really comparing apples and apples, and we're not increasing the number of parameters in the neural network to make it aware of more features, because that would be, in some sense, this would be a little bit unfair, because with more parameters, of course, the network can also learn different representations. And now let me talk about a brief plan here. So we'll first be assessing the expressivity of our neural network on synthetic datasets. Then we'll talk a little bit about the performance on datasets without node features, and then we'll assess the predictive performance finally on benchmark datasets. And again, I'll walk you through it a little bit, but I just pick out some of the highlights of this technique, which I find to be the most useful or the most interesting here. Now, the first one is the expressivity or the predictive performance on a synthetic dataset. You can see that this dataset is aptly named necklaces because it looks a little bit like a necklace that you can put on or that you can put off. And when we take a look at the predictive performance with some architectures here, we can see that a GCN architecture requires quite a considerable number of layers to approach useful predictive performance. So in order to tell you whether you have this type of graph or this type of graph, you need, let's say, at least 6 layers in order to be at, let's say, 80% or 85%. Whereas with our topology-based graph neural network, which is this blue line here, we get almost perfect performance right from the beginning, making it a very good example of what to do and with topological features. Likewise, you can also see that the comparison method, this very, let's say, established WL test, the Weisfeld-Lehmann test, also doesn't perform that well. It requires quite a number of iterations or quite a number of calculation steps to get up to useful performance here. So this was kind of a very useful and very encouraging result that we found. Let's take a look at what else we can do with this data set. So One experiment that we wanted to do at the very beginning is we wanted to take a look at how well we can classify graphs or nodes based on structural features alone. This is motivated by a certain observation, namely that existing data sets that we have tend to leak information into node attributes. So they already give you some information about the node attributes. For instance, if you have a molecular data set and you know that you have a carbon atom, then it's quite likely that the carbon atom will be part of a cycle structure, because that's what molecules do. But this decreases a little bit the utility of a purely topological approach. And of course, the molecule example is not even the worst one. There are some data sets which really contain a lot of structural information already by the node labels or by the node attributes. But to really assess how well they would fare if you only look at the connectivity, we started replacing all node features by random node features. And now I don't want to talk about all the numbers in this table, but I want to give you a way to compare the performance of our method with the baseline method. So the baseline method, as I said, is the GCN with 4 layers, because we take one of those layers and replace it by our layer. So when we mention the TopoGNN 3.1, this means that we have 1 topological layer and 3 GCN layers still. And we can see that in contrast to this baseline, we are always outperforming it. So we always considerably improve over the baseline by making the network topology aware. We're not always the best performing method on these data sets, even if other networks are not that well tuned towards topological features, but we're doing our best here. So this is also very encouraging, and it demonstrates that there is a fundamental utility in having topological information, as long as the graph node features are not informative, I should say. Once they start being informative, it looks a little bit different. Namely, we obtain these results on the classical benchmark data sets in graph classification, where this time we didn't change the node attributes, but we just took everything the way it is. So again, here we see that we still improve the baseline classification performance. So in contrast to this line here, we are still improving on those features, except for in some rare cases where we either can't get the network to fit, as in enzymes, or where we have some high standard deviation such that it's really a little bit tough to say whether we are on average better or not. But at least it demonstrates again that we can improve the expressivity of a baseline architecture by adding more topological information. But of course, the choice of our baseline architecture also fundamentally, to some extent, limits what we can achieve in the end. So you can see, for instance, that the GAT4 method, which is a graph attention network, is really performing quite well. Likewise, a gated GCN. So there's all kinds of different modifications to do well on those benchmark data sets, and it's tough to beat all of them in the same go, which is admittedly not our goal in the first place, but we wanted to demonstrate that we can improve the expressivity of an existing architecture quite substantially. Now, where do we go from here now? So this is kind of the first project I wanted to talk to you about. I have a second one that is a little bit shorter later on. The first observation I want to make here is that there's this old adage which says, if all you have a hammer, everything looks like a nail. So I have the feeling personally that some of our datasets might actually stymie progress in GNN research, because their classification does not necessarily require structural information. So if a lot of the edge information is already available in the nodes, then you don't really need to consider the edges. But this also means that you don't need to consider the rest of the graph structure, and you could just do the prediction on the nodes themselves. And this is a little bit problematic because it makes you focus on the wrong things. Classifying a graph should fundamentally also be about incorporating information about the edges. This is what we need to work towards as a community, I think. That being said, we know that higher order structures in graphs, such as cliques, for instance, can be crucial for discerning between different graphs. Michael Bronstein has a recent preprint on this where he and his group imbued graph neural networks with additional features based on cliques and other higher order information from graph neural networks, from graphs, pardon me. And this turned out to be really crucial in improving classification performance. Of course, the question for us is that maybe we should integrate this now into GIN architectures instead, because the GIN is actually known to be quite good in performing classifications. And so maybe this would be the natural comparison partners here. And likewise, and this might be interesting for some in the audience because it's not exactly my forte, but I would be interested in learning whether there are conditions under which we're guaranteed to learn an appropriate filtration function, so an appropriate view of the graph. Currently, we only have the theorem that tells us that these functions exist, but this doesn't tell us whether we end up learning them. But mostly, I think the question that we want to answer, and that we partially answered in this preprint, is what do we actually gain from learning a filtration function, as opposed to having a predefined function that goes through our graph and calculates topological features? I think the answer is that we gain a lot, because we also have some comparison and ablation studies in the preprint that discuss these aspects. But nevertheless, it's a little bit of an open question whether this can be defined or decided in learning theory terms. So are there any questions about this part? If not, then I'll be happy to move on. And I want to talk to you about one project that is actually going to be presented tonight by Leslie at KDD. So if you're also at KDD and have access to their portal there, so please tune in I guess about an hour from now. This paper is called Filtration Curves for Graph Representation, and it's a joint work with Leslie and Carsten. In this paper, we kind of looking again at this question of what do we gain by not only looking at the graph at a single scale or at the graph at one point in time, but what do we gain by looking at the graph construction process using some additional filtration function or some additional filter function that we saw before. So previously we saw that given a filtration of a graph dataset, so this perspective of assigning some function values to the vertices and then going along these function values and looking at topological features, we saw that with this technique, we can easily obtain these persistence diagrams, these topological descriptors. Now, these descriptors can also be conveniently represented by a curve representation that is known as a Betti curve. This Betti curve is essentially obtained by taking the diagram, doing a simple transformation on it, which turns every point into a line, and then just checking the vertical intersections of these lines with another vertical line. Now, but the question for this project was, if we don't use a normal filtration function, what do we gain by using a more general descriptor function here? So something that tells us something about the graph. This might sound a little bit vague, and I apologize for this vagueness here. It'll become clear in a simple example. So suppose we have a graph like this one here. And now suppose we have some way of filtrating it, which means that we have some way of looking at this graph over a growth process. And now let's assume that we're interested in, let's say, counting the node labels. So we would be using the node label histogram as what we call a descriptor function. Now, in every step of the filtration, also in every step of the growth process of the graph, we just count the number of nodes and assign them to their respective buckets. So in this case, in this filtration step, we would have one red node and two blue nodes. Then we add something, and suddenly we have another blue node, and suddenly in the last step, we have another blue node and another red node. Now, this gives rise to two curves, namely one curve for the red nodes and one curve for the blue nodes. And we obtain this graph by updating it at every step of this function. So again, moving from this graph here, we can start here, we gain 1 point in those two functions, in those two curves, another point, another point, another point. This leads to the following functions, which admittedly, these curves don't look that informative because of course that's an illustrative example, but you can see that at the beginning of this filtration, we had one red node, and at the end we have two red nodes. And here in the beginning, we had two blue nodes, and at the end we have 5 blue nodes. Again, as I said, this doesn't look too interesting, but for real graphs can do a lot with this. Specifically, we can do the following. We can pick a function to induce some graph filtration. So any graph descriptor function will do. We could, for instance, use the weights if a graph has some, but we'll also see some examples about this. Then we pick some descriptor function, so something that turns our graph into a high-dimensional feature vector. And this could either be a graph neural network if we want to be really fancy, but in our example, we actually looked at very simplistic functions and just used the node label histogram count. And now we can evaluate this function f alongside the filtration, alongside this growth process. And this turns the graph essentially into a high-dimensional path. So a high-dimensional path that we obtain by concatenating all these individual representations along the length of the path. And this path now carries multi-scale information about G. Multi-scale meaning here that we're not only looking at G as it is given to us, but we're also looking at G under different filtrations, under different perspectives of this descriptor function. Now, without going into too many details here, these curves also have some nice properties, because we can already show that there is a well-defined mean filtration curve. So this is a great thing to do if you this is a great thing to have if you want to do hypothesis testing, for instance. So if you have two sets of graphs and they have different labels and you want to know whether one is statistically significantly different from each other, then you could use those curves to assess this fact. This is something that we showed in a previous work. But I want to talk rather, as we come towards the end of the session, I want to rather talk about the choices that we have for these descriptor functions. So in our experiments, we evaluated a lot of things. We evaluated different filtration functions, so different perspectives on the graph. We used native edge weights. We used something like a degree function. We used a curvature calculation, Olivier-Ricci curvature, which is a really hot topic now in graph neural networks research. And we used a heat kernel signature, which is a well-known descriptor arising originally in computer graphics and mesh comparison. As for the descriptor functions, we actually used two very simple ones, namely the node label histogram, so just counting how many nodes of a certain label there are, and the number of connected components, which is kind of closing the loop here, if I may have a small pun, because it's very much nicely connected to what we talked about in the first project. And the important thing I want to stress here, in comparison to the previous project, all the filtration functions are shallow here. So nothing deep is going on. We are not learning a specific function from the left-hand side, but we're just picking out one and seeing how far we will go with this. And the overall question that you can answer here is that how far can you actually go with this? Is this really competitive? The answer is sort of. When you look at the table, you will find that our method in the last row performs quite well in many of the data sets. It isn't the singular winner in all of them, but for datasets with native edge weights, it is definitely competitive. In datasets with non-native edge weights, however, the performance is a little bit lukewarm, but nevertheless, it's always among the top performing methods. And we can even show that by looking at the absolute distance to the accuracy of the best method. So if we take all the methods that are out there and we calculate the absolute distance of every method to the best performing method here, we gain some information about the spread or about the overall stability of a method. Ideally, you would want to be here. You would want to be at 0, and you would want to have 0 variance for your method, because that would mean that you win in all the data sets and in all the cases. We are here, which I think is quite good, which illustrates that while we are not always the best performing method, as you can see from the spread here, we are still kind of consistent. We don't have a lot of variance in our predictions, and we're still among the most competitive methods, and maybe among the top 2, top 3 ranking methods for this, which is astonishing, because when you think about it like this, these are all kinds of very complicated comparison partners, graph neural networks, a WL procedure with optimal assignment, some specific kernels for specific graph structures. And we just come there and we are saying, oh, well, we calculate a curve based on some kind of descriptor function, and then we take a look at how well it performs overall. So this is really astonishing, and it really shows that this might constitute a very strong baseline that people should compare towards, because in contrast to all those other methods, it also has a significantly smaller number of parameters that need to be trained. So it's a very cost-effective way of representing your graph. Now, with this, I want to finish now and want to talk about some lessons learned from this project and from the other project. So the first one is that these filtration curves that I showed you in the previous slides, even the ones based on very simple descriptors, such as a node label histogram, they are surprisingly competitive. But moreover, this also means that these multi-scale aspects that we saw before, they can be translated to other domains. So they can be used to drive graph classification performance. They can be used to improve graph classification tasks and making graph neural networks aware of topological features. There's all kinds of new things going on that can make this field much more richer. And specifically, even we showed that extensions based on learned filtrations are possible. So we're not the first ones, I should stress that. We're not the first ones to show that one can learn these representations. There's lots of other work out there, and in particular in the TDA, in the topological data analysis community, there is one work called graph filtration learning that is already handling the learning of a single filtration. But we are also showing the value of having multiple filtrations, of having multiple views of the graph. But last, and I think this is the point most dear to my heart, we also need better data sets that contain more structural information in order to be truly successful in the future in graph neural networks, because the current benchmark data sets, they force you in one direction with respect to optimizing a method, and that might not be the most fruitful direction for our research landscape. But that's, of course, a little bit of conjecture. So thank you very much for your attention. I'm happy to take any questions now if you have them.
Thanks for the talk. Got a couple of questions actually. Maybe I just ask the first one and then maybe somebody else. So about the whole, so if we're learning filtration curves, right? So we're learning, I guess, So I'm not completely clear on how we actually learn this given a data set. Like as I would understand it, likewise, I would have kind of I would define some function at the beginning, but I'm not sure how you would learn that in the process.
So the filtration curves, they are, when I say learning, this is maybe too much of a stretch. So the filtration curves are obtained, I should say, by picking a filtration function. So for instance, we could just take the native edge weights if a graph has native edge weights, and by picking a descriptor function, such as the node label histogram. And then out of this calculation, we get something like this here, something like the bold curve in the middle. And this is a curve that we can use, that we can discretize, for instance, and plug into a random forest. Or we could, if we feel more fancy, we could use a kernel representation, so a similarity measure on the space of those curves, or even a distance measure based on those curves, and use that to do the classification. So the curves in itself are actually not learned. That's I should.
Okay. Yeah, the misunderstood that. Yeah, and then one other thing is also on the I forgot the name, not the filtration, but for example the label histogram, right? You said you create that, well, basically similar to or in the graph construction, right? You construct the graph from the initial nodes, you add on the native, like the edges by the native edge weights, right? So how do you actually then build up your node label histogram, right? Because technically all nodes are there from the beginning, right? So do you say like, okay, when they belong to a component that is created, then we add them, or?
No, the ordering, you're absolutely right. The nodes are technically there from the beginning, but we use the filtration function to impose some kind of ordering in which we add the nodes or the edges. And we use that to specify how to count them. So if your graph, for instance, has, let's say, no native edge weights and you use the degree function, then nodes will be added in ascending order of their degree. And this means that the node label histogram changes over that time. But That's also a very important point to make here. This is why I'm stressing this so often. These functions are really shallow, so there's nothing, they're not task specific yet, which is exactly why their performance is so surprising. Because you wouldn't expect that, right? You wouldn't expect that just by counting the node labels across various scales of your graph that you would gain this this sort of representation that is actually useful.
Right, thanks.
Of course, welcome. Any other questions that you have? Otherwise, I should also say this to anyone who is watching this afterwards. Feel free to reach out either over Twitter, so I'm at pseudomanifold, or over email. So I have a bunch of profiles that I connected with my Twitter account. You can also find me in on the ETH website or on the with my personal website. So I'm always happy to discuss things that are related to topology, graph neural networks, graph classification, these sort of aspects.
Actually, I have another question. So all the tasks you did in the end, right? All the graph classification tasks, are they all? Can you just tell a bit more about what the specific task was? Are they, or do they vary over a wide range of different kind of classification tasks, or are they all, say, yeah?
So I actually don't know all these tasks by heart, but most of the time these are binary classification tasks or multi-label classification tasks. So you get a graph that is, for instance, a molecular structure, and then you're supposed to classify this structure here. So, for instance, proteins is about classifying protein structures. In some of the other data sets that we saw in the previous project, let me just walk back to that. We have, for instance, the Reddit dataset. The Reddit dataset is a binary classification dataset in which you're taking essentially graphs that are created from Reddit discussion threads, and so it's kind of a social network dataset that has to be classified. Then DD and enzymes are molecular datasets again, with I think multi-class classification. But all of those, I should stress, are known as benchmark datasets now to the community, and they're sufficiently large to be non-trivial, but they're also not too large to impede new method development. So you don't need necessarily a multiple GPU clusters in order to train your model. So this is what makes them kind of appealing. But as I said, there's also this dark component hiding there, because many of those network data sets can be easily classified using rather simple methods. So it doesn't actually, if you just want to solve the classification task, you don't necessarily need a GNN. But well, it's kind of the best that we currently have. Although I should stress there are bigger data sets, and there are even bigger data sets, but I'm not super familiar with all of them to have an informed opinion on whether they are fundamentally structure driven or fundamentally node label driven, or a mixture of the two of them. Any other questions or comments?
I have a question, but I don't know if it's an off-topic question.
Go ahead.
What if I need a specific moment of the filtration process? There is a way of using your filtration curves to figure out which moment in the filtration is better to perform a node classification, for example.
Yeah, this is technically possible. So that's a very cool idea. We haven't actually tried that out, I think, but I have to ask Leslie about this. But it would indeed be possible, since we have a vectorized representation of those curves. We could essentially treat them as features, and we could see what feature contributes to the overall prediction output, and that would make it possible for us to analyze whether all the features or all the time steps or all the filtration steps are equally important or not. So I think Leslie, now that I think of it, I think Leslie ran experiments which showed that there is not a direct clustering of this information. So it's not like there's only one or two steps that are relevant. So it's not a sparse representation, but the network or the model typically draws from a lot of the filtration steps. But this is very much, I should stress, this is very much data set dependent. But it's an awesome suggestion. We'll definitely might follow up on this. So please, if you're interested in this, please feel free to reach out to us. That would be a very nice follow-up work or a nice project.
Thank you. Okay.
You're welcome.
Thank you.
Any other questions?
I'm just wondering, like, I mean, this is completely off the grid and off topic just because of a paper I read a couple of days ago. Wondering if you could use this within, say, like there's a whole bunch of papers on using reinforcement learning to develop, well, intervention strategies on graphs, say influence maximization, right? I train an reinforcement learning model that uses a GNN as its backbone, and that then, well, decides on a couple of actions on certain nodes, for example, like influence them to maximize the influence over a whole graph, right? And I'm just curious if you think like this, because that basically to a great degree ignores topology as well. And whether that one could implement or use something like this in there as well.
I mean, I have to stress that I'm not super familiar with reinforcement learning approaches at the moment, but I think that having a, let's say, topology-based loss term or a topology-based regularization term for these sort of operations could be really useful. So for instance, you could use these persistence diagrams to, let's go back here a while, oh, this is a real while. You could use these diagrams to assess to what extent you're deviating from a previously known structure, for instance. That would be one possibility. That would definitely haven't. So
which might then give good information to the learner, I guess, right?
Yeah.
So, yeah.
We have experimented with these sorts of considerations in a previous paper on autoencoders, where colleagues and I developed a loss term for regularizing the embeddings of high-dimensional data sets. So this might turn out relevant here as well. This is a really good suggestion. Thank you. Anything else I can discuss with you? If not, then maybe I'll stop the recording here and